The world needs energy. Our homes and businesses rely on a constant energy supply. For centuries we relied on fossil fuels. Fossil fuels pollute our planet. These gases contribute to climate change. We need to find cleaner ways to power our world. Renewable energy sources offer a promising alternative. Unlike fossil fuels, they do not produce harmful emissions. This makes them sustainable and environmentally friendly. Solar energy is already making a difference. Solar panels are becoming increasingly common. They are silently converting sunlight into usable energy. This shift towards solar energy is a positive step. It reduces our dependence on fossil fuels. Researchers are constantly working on improving solar technology. They are making solar panels more efficient and affordable. As technology advances, solar energy will become even more accessible. Governments, businesses, and individuals all have a role to play. By embracing solar power, we can create a brighter future for generations to come. The sun is the ultimate source of energy for our planet. For centuries, humans have harnessed the sun's energy for various purposes. Today, we have developed sophisticated technologies to capture and convert sunlight into electricity. This is the essence of solar energy. Solar energy relies on a simple yet powerful concept, the photovoltaic effect. This effect occurs when sunlight strikes certain materials. These materials then release electrons, creating an electrical current. This discovery revolutionized our ability to harness solar energy. It paved the way for the development of solar panels, also known as photovoltaic (PV) panels. Solar panels are designed to maximize the capture of sunlight. The sun dominates our sky. It is a massive ball of hot gas. Deep within its core, the sun is a raging furnace. This process releases an incredible amount of energy. This energy radiates outwards from the sun in all directions. Earth only receives a tiny fraction of the sun's total energy output. Yet this small fraction is enough to power all life on our planet. The sun's energy is essential for life as we know it. By harnessing even a small fraction of this energy, we can meet our growing energy needs without relying on polluting fossil fuels. Sunlight may seem simple, but it is actually quite complex. It is made up of tiny packets of energy called photons. Photons travel at the speed of light. They carry different amounts of energy depending on their wavelength. Visible light, the colors we see in a rainbow, is just a small part of the electromagnetic spectrum. When sunlight reaches Earth, it interacts with matter in different ways. Some materials absorb sunlight, converting the light energy into heat. Photovoltaic cells, the building blocks of solar panels, are designed to absorb photons and convert their energy into electricity. This process, known as the photovoltaic effect, is the key to unlocking the sun's energy. Photovoltaic cells are made from materials called semiconductors. Silicon is the most commonly used semiconductor in solar cells. Semiconductors have unique electrical properties. When a photon strikes the surface of a photovoltaic cell, it can transfer its energy to an electron in the semiconductor material. This energized electron is now free to move around. It creates a flow of electrical current. This is the basic principle behind how solar panels generate electricity. The efficiency of a solar panel depends on how effectively it can convert photons into electrons. Scientists and engineers are constantly working to improve the efficiency of solar cells by optimizing their design and materials. Not all photons that strike a solar panel will generate electricity. Solar panels are marvels of modern engineering. They are able to harness the energy of the sun and convert it into usable electricity. The key to this remarkable feat lies in the heart of each solar panel: photovoltaic cells. These cells, often referred to as solar cells, are the engines that drive the entire process. Photovoltaic cells are made from special materials called semiconductors. When sunlight strikes a photovoltaic cell, it sets off a chain reaction that releases electrons within the semiconductor material. These freed electrons are then harnessed to generate an electrical current. Each photovoltaic cell produces a small amount of electricity. To generate a usable amount of power, multiple cells are connected together in a solar panel. Modern solar panels can achieve efficiencies of over 20%, meaning they can convert more than 1/5 of the sunlight that hits them into usable energy. To understand how photovoltaic cells generate electricity, we need to delve into the world of atoms and electrons. Atoms are the basic building blocks of matter. They consist of a nucleus, made up of protons and neutrons, surrounded by a cloud of electrons. Electrons orbit the nucleus at different energy levels. In a conductor like copper wire, electrons are loosely bound to the atoms and can move freely throughout the material. This free movement of electrons is what allows electrical current to flow. Semiconductors, the materials used in photovoltaic cells, fall somewhere in between conductors and insulators. When a photon, a tiny packet of light energy, strikes a semiconductor material, it can transfer its energy to an electron. This process is known as the photoelectric effect. The efficiency of the photoelectric effect depends heavily on the type of material used. Pure silicon, while a semiconductor, isn't very good at releasing electrons when hit by sunlight. To enhance its efficiency, silicon is doped with other elements. Doping is a process of intentionally introducing impurities into a pure semiconductor material to alter its electrical properties. Two types of doping are used in photovoltaic cells, N-type and P-type. N-type doping involves adding an element like phosphorus, which has an extra electron in its outer shell compared to silicon. P-type doping, on the other hand, involves adding an element like boron, which has one fewer electron than silicon. These doping processes are crucial because they create an imbalance in the electrical charges within the silicon. The magic of a photovoltaic cell happens when an N-type silicon layer is brought into contact with a P-type silicon layer. This creates a region called a p-N junction. At this junction, the free electrons from the N-type side are attracted to the holes in the P-type side. This movement of electrons and holes creates a region at the junction depleted of charge carriers, called the depletion zone. However, when a photon strikes the cell, it can knock an electron loose in the depletion zone. Due to the electric field established by the p-N junction, this freed electron is propelled across the junction toward the N-type side, while the hole it leaves behind moves toward the P-type side. This creates a flow of charge carriers, which is essentially an electrical current. When a solar cell is connected to an external circuit, this current can flow through the circuit, providing power to devices or being fed into the electrical grid. The heart of a solar panel, the photovoltaic cell, relies heavily on a specific element, silicon. Silicon, the second most abundant element on Earth, is found in sand, quartz, and many rocks. But it's not its abundance that makes silicon special, it's its unique electrical properties when refined. In its pure form, silicon acts as a semiconductor. This means it's neither a good conductor of electricity like copper, nor a good insulator like rubber. It lies somewhere in between, allowing for the control of electrical current, which is critical for the photovoltaic effect. To make silicon suitable for solar cells, it undergoes a purification process. The raw silicon is heated and chemically treated to remove impurities, leaving behind a highly pure form, often called solar-grade silicon. Creating a solar cell from purified silicon involves adding impurities, a process called doping. This establishes the electric field, essential for electricity flow. N-type uses phosphorus, P-type uses boron. Together, they form the crucial p-N junction. While silicon dominates the solar industry, it's not the only material being explored for solar energy conversion. Researchers are constantly looking for new materials and technologies to improve efficiency and reduce costs. One promising area is thin-film solar cells. These cells use significantly less material than traditional silicon cells, making them potentially cheaper to produce. Examples include cadmium telluride, CDTE, and copper-indium gallium selenide, CGs, solar cells. Another exciting development is perovskite solar cells. Perovskites are a class of materials with a specific crystal structure that are incredibly efficient at absorbing sunlight. They have the potential to surpass silicon in terms of efficiency, but challenges remain in scaling up their production and ensuring their long-term stability. The moment a photon knocks an electron loose in a solar cell, the journey of solar electricity begins. This freed electron, propelled by the electric field within the cell, creates a flow of direct current, or DC, electricity. DC electricity flows in one direction, much like the current from a battery. However, our homes and the electrical grid operate on alternating current, or AC, electricity. AC electricity periodically reverses its direction, which is more efficient for long-distance transmission. To make the solar energy we harvest usable, a crucial transformation must occur, converting DC electricity into AC electricity. Before reaching the inverter, the DC electricity generated by the solar panels travels through a system of wires and components. This system typically includes blocking diodes, which prevent current from flowing backward and potentially damaging the panels. The heart of the DC to AC conversion process lies within a device called an inverter. Inverters are electronic devices that transform the DC electricity generated by the solar panels into the AC electricity used by most appliances and the electrical grid. Inverters achieve this transformation through a clever combination of electronic switches and circuitry. These switches rapidly change the direction of the DC current, effectively creating an alternating current. The inverter also smooths out the resulting AC waveform, making it compatible with the grid's frequency and voltage requirements. The efficiency of the inverter plays a significant role in determining the overall efficiency of the solar energy system. Modern inverters boast high efficiencies, typically exceeding 95%, minimizing energy loss during the conversion process. Once the DC electricity has been converted into AC electricity by the inverter, it is ready to be used within the home or fed into the electrical grid. One of the remarkable aspects of solar energy is its ability to seamlessly integrate with the existing electrical grid. Once the solar inverter has converted the DC electricity to AC electricity, it can be fed back into the grid, allowing homeowners with solar panels to become energy producers. This grid integration is facilitated by a device called a net meter. The net meter tracks the flow of electricity between the home and the grid. When the solar panels produce more electricity than the home is consuming, the excess energy is sent back to the grid. The net meter runs backward, indicating that the homeowner is effectively selling electricity to the utility company. Conversely, when the home's energy consumption exceeds the solar energy production, electricity is drawn from the grid and the net meter runs forward. This two-way flow of electricity, often referred to as net metering, allows homeowners to offset their energy costs and potentially earn credits from the utility company. It also contributes to a more resilient and decentralized energy grid, reducing reliance on centralized power plants. The allure of solar energy hinges on efficiency. How effectively can we transform sunlight into usable electricity? This efficiency dictates our energy harvest. Solar panel efficiency is expressed as a percentage. It represents the proportion of sunlight converted into electricity. Modern panels surpass 20% efficiency. Some technologies push beyond 23%. While solar panel efficiency provides a useful benchmark, the actual energy output is influenced by various factors. Understanding these factors is crucial for optimizing performance. Solar irradiance, or sunlight intensity, is a primary factor. Locations with abundant sunshine receive more energy. The angle of sunlight affects energy production. Temperature impacts performance. Excessive heat reduces efficiency. Shading can significantly reduce output. As we've journeyed through the intricate workings of solar panels, we've uncovered a profound truth. The power of the sun holds the key to a brighter and more sustainable future. Solar energy, once a futuristic dream, has blossomed into a tangible reality, transforming our relationship with energy and our planet. The transition to a solar-powered future is a journey we've already begun. Every home powered by the sun brings us closer to a world of clean, abundant energy. The path ahead requires collective action. Governments must incentivize solar adoption and foster innovation. Businesses must embrace solar energy, investing in a cleaner future. Individuals can make a difference, embrace a sustainable lifestyle, advocate for renewable energy policies, support businesses prioritizing sustainability, educate about solar power benefits, become ambassadors for a brighter future. The sun, our source of life and energy, harness its power for a sustainable world. The future is bright, powered by the sun.